Hey, good morning, everyone. Welcome back. How are y'all doing?
Doing all right.
All right. All right. Today, 7.4 arc length, 7.5 surface area. Next class, I'm going to try and do maybe one topic from applications. I have some options when it comes to 7.6. It's too much material to cover the whole thing because it would take us like 2 days. So I have to kind of pick what I want to talk about. I can talk about work. That's an application to physics. I can talk about hydrostatic pressure. I can talk about moments and centers of mass. There's all kinds of things I can talk about. I'm not sure what I'm going to do yet. So I'm going to just pick one thing and just talk about it. All it is just to show you how we can use integrals, in applied settings. So when you take an engineering course, you're going to use, the integral to do like center of mass, moments of inertia, things like that. So that's the plan. Okay. 7.6 is not on our schedule. When you look at our schedule, what we're supposed to do, I don't have 7.6 reserved in here for a certain day. I just try and squeeze in maybe one thing from it. So just if I give you a homework assignment over it, I'll give it to you in class. All right. Okay, let's get down to business. 7.4 arc length and surface area. I want to remind you that in your Canvas files, there is a document. The document is called Chapter 7.4, 7.5 arc length and surface area summary. And it basically has all the different formulas that you need to be able to do arc length and surface area. So I'll be referring to this today. But to get us motivated, to get us started, let's take a look at what we're going to do in 7.4, which is to find the arc length of a function. So up to this point, if you have a function or if you have two functions, well, let's just go back to one function. You can find the area underneath the curve, right, down to the x-axis. You could even rotate that around the x-axis. You could rotate it around any horizontal line. You could rotate it around the y-axis or any vertical line using either the method of washers or shells, depending on whether or not you have a function of x or a function of y, right? That's what we can do up to this point. So now what we want to do is talk about the arc length of the function. So I have a little sine curve here for you. There's a little sine curve. And what I'd like to know is if I were to somehow take that curve and look at it as like a string, okay, a string or a wire that's on a page or on a paper or on a surface, if I were to take it and just stretch it out, right? Stretch it out, could I measure how long it is? All right. So like if you're walking along that path, what is the length or the distance you would travel? Okay. And I should be able to do that for all sorts of different curves, right? It doesn't have to be a sine curve. That's the idea. Okay. That's the idea. Could we find that length? So here's the approach. We go back to our good old picture. By the way, Joshua, I put that in room 213 at Northwest Vista College for you. And they will be there tomorrow, 8 a.m. to like 5 p.m., I believe. But I do believe they do a lunch break between 12 and 1. They said they may or may not be there. So I'm just giving you a heads up. If you go there between 12 and 1, that you might have to wait. Okay.
No worries, I'll hang out in the library or something. Thank you.
Yeah, it's in a little box. It has your name on it and everything. So, all right. Okay. So we start out with the general picture, right? We have some function. Let's call this f. And in this case, I'll say f of x because that is a function of x. Let's start it out at some arbitrary point A, and let's end it at some arbitrary point B. And what we'd like to know is if we stretch this out, how long is it, right? So the way we go about this is we kind of do what we did before with, how we've been coming in here with these arbitrary rectangles, right? We do a rectangle like that. And we'd use that to find the area, or if we rotate around the x-axis, we'd create some sort of washer. We're gonna do kind of the same idea, but a little bit different, okay? Watch what I'm gonna do. I'm not gonna do a rectangle. Sorry, I should have told you I'm not gonna do a rectangle. What I'm gonna do is I'm going to take one little small section of this, okay? And I'm going to zoom in on it, right? Zoom in on that. And so what you'll see there is the curve, right? The curve. And I'm only zooming in on certain little sections. So you can almost imagine like I did a rectangle. And I'm only just focusing on this top edge right there. But the blue part is the curve, okay? Now the distance from the bottom corner of that curve to a line dropped straight down and straight across at a 90-degree angle like this distance will be dx, because that's the width of the rectangle. Y'all agree? That's the width of the rectangle. Okay, I'm trying to approximate how long that blue piece is. So what I'll do now is I will connect the end point here to the end point here with a straight line. Now remember, the blue part is a curve, right? So a straight line and a curve aren't necessarily the same thing, but would you agree that the smaller this rectangle gets, right? The more narrow it gets, the less error I have, right? The error that I have is this region between here. That's my error. Between the length of the red one and the length of the blue one are different, but the amount of error I have is the fact that there's that gap between them. But the smaller the rectangle gets, do you agree the smaller the error would get? The error would eventually, if you get narrow enough, the error would go away, which is exactly what we did when we did the area of rectangles, right? We said we're going to have an infinite number of rectangles, which means that the width of the rectangle would go away. I mean, would go to 0. So if I can find a way of approximate or find a way of finding the length of the red one, then when we do the limit and have an infinite number of these, it will essentially become the length of that blue piece. Do y'all buy that? In the limit, the error will vanish.
I got a question.
Yes.
Okay, I know when we do, I always forget the name of it, but it's f of x plus h minus f of x over h. We use that to get the slope. Is that kind of similar? Where like because I guess that's kind of the that's the slope of a single point, but instead of getting the distance between 2 points on a curve, it's almost like the infinitesimal distance of like a single point when you add that variable. Or is it kind of like the same thing, but with the like what you're doing here?
Yeah, well, actually, we are going to need the derivative here. Exactly. We are the derivative because so what you're talking about, the limit h goes 0, f of x plus h minus f of x over h, that's the derivative from Cal 1.
Okay.
So yes, we are. So we are going to need it. I'm about to show you how we're going to use it, but I want to make sure everyone at least buys into the idea that if I can find the length of the red one, then I can just come up with a formula for that length and then add up all the lengths using the integral. So like we've been doing, this is the common theme, right? It's like we find a formula for either the area of a little piece or the volume of a washer or the volume of a shell, and then we add them all up with the integral. I want to find the formula for the length of that red line segment. And if I can find a formula for it, then I'll use the integral and add them up. That'll give me the total length of the curve. So as long as we all buy into that, then now I need to set forth in trying to find a formula for the length of the red piece. Okay. So I'm going to remind you now that this curve, right? Normally we write y equals f of x, right? That's the way the notation we use. Y is some function of x. Back in Cal 1, if we took the derivative of y with respect to x, by definition, that's f prime of x, right? That's the definition of what dy dx means. It means take derivative, right? Which we could talk about the limit, but we're going to go beyond the limit now because when we're in Cal 2, when we take derivatives, we definitely don't want to go to the limit definition. We want to use our shortcut rules, power rule, product rule, quotient rule, chain rule, all that, right? But it is still the derivative, right? So that's what dy dx means. So why am I showing you this? I'm showing you this because remember on this triangle I drew, we said the width of it, right? From here to here, we said was dx. I would like to know how long this red piece is. Let's call that, let's call it L, okay? I want to know what L is. I have one side of a right triangle. The other side of this right triangle, that means from here to here, that's my infinitesimal change in y. So that's dy, isn't it? If the left and right is your infinitesimal change in x, dx, then the up and down is your infinitesimal change in y, which is dy. And we have a formula up here that has dy in it, right? See the dy? If I multiply both sides by dx, I have a formula for dy. With me?
I'm just having trouble visualizing why you're using a triangle in this case for, yeah.
Because I'm trying to find the length of this blue piece right here, right? I'm trying to find the length of this blue piece. So I just took like a zoomed in portion of it, which means that there's 2 points connecting it. And I'm just saying that if I try and get from one point to the next point on the x-axis, this will be my change in x. And if I try and get from that point up here, this will be my change in y. And so if I'm trying to figure out how long the blue piece is, I can approximate it by creating a right triangle here. And the red hypotenuse would be really close to the blue piece, especially when I let the width, the dx, go to 0. Am I still not making sense with that?
No. I get that, but when you, it's mostly when you put the derivative portion over there in the opposite, and you put the dx on the adjacent. If that kind of makes sense, because the function that you have, it's not necessarily the derivative yet, is it?
The function that I have. I'm trying to understand your question. I'm giving you an arbitrary function, right? And I'm saying if I give you an arbitrary function and we say, okay, let's define y to be equal to that function, then the derivative of y with respect to x is just f prime of x. And then if I take this and solve it for dy, let me do this. Let me do this. Just forget all this for a minute, okay? Just forget all this. Just go to this picture. Do you agree with this picture? That the width, the bottom part of that right triangle is dx and the top is dy. Y'all okay with that? Change in x, change in y. And then L would be the hypotenuse, the red hypotenuse. By the Pythagorean theorem, right? You have a squared plus b squared is c squared. Y'all agree with that?
I get it now. I get it.
Okay, I have this plus this must equal this, right? And I was trying to find a formula for L. So let me just take the square root on both sides. So now I have a formula for the length of that little infinitesimal piece, right? I want to add them all up. So I'm going to bring the integral in. The integral is going to start at A and end at B because I want to move across and start adding up all these. It's like I'm doing a bunch of little triangles in here that have red hypotenuse all in here, right? A bunch of little triangles, and I'm going to do an infinite number of them and add them up. And so my integral will go from A to B, and then what am I adding up? Well, my L's, right? I need to add up my L's, which is the square root of dx squared plus dy squared, right? That's where we are. We all good with that? The problem
would that
with
be?
this, go ahead.
Oh, I was going to ask what that would be integrated with respect to. Is that
Yeah,
what you're
so-
about to jump onto?
Yeah, so right now when we look at that, we're like, well, wait a minute, hold on. Every integral we've had before has had like a dx out here, or it's had like a dy out here, right? Like when we were doing the area, we had the width of the rectangle was the dx, or, you know, we would always have something out there, wouldn't we? We don't have anything out there right now. We have this. That's new. It's like we haven't seen that before. Got it? What do we do with this? So now let me go back to this. If f of x is our y value of our function, then dy dx would be the derivative of that function. And if I solve for dy, I get dy is equal to f prime of x dx. Follow? I'm going to take this f prime of x dx and I'm going to replace dy right here in this expression with it, which would become this integral a to b square root dx squared plus, now dy we just said was f prime of x dx, but I've got to square that. Okay, now that may not look better, but watch. Integral a to b square root. This is dx squared plus, now when you square this, because there's multiplication between the f prime of x and the dx, I can square each one. So it would look like this. It would be the derivative of x, that thing, I'm putting in brackets to match the book, that thing squared times the dx, but then that thing squared. Y'all still with me? This square, I'm just squaring this. What do both of these terms have in common? What do they both have in common? There's a GCF in both of these.
DX?
dx squared, right? The dx
Yeah.
squared. So I could then write that as integral a to b square root of, I could factor out the dx squared, and what I'd be left with here, if I pull dx squared out of this, I'm left with a 1, then plus, because there's a plus sign here, and then I pull the dx squared out of this one, which leaves me with the f prime of x, that thing squared, right? But dx squared underneath the square root can come out of the root as a what?
Just DX.
Just a dx. And that dx now is outside the root. And inside I still have 1 plus the derivative of f squared. And then I can just slap the dx to the back. And now you have something that looks more familiar to you. Okay, so that root ends right there. This is our formula. So let me try and recap what this formula is saying. If somebody gives you a function, okay, y equals f of x, and they give it to you on some interval a, b, and they want you to figure out how long it is, right? How long is that thing? What you're going to need to do is you're going to need to take the derivative of that function, okay? You're going to need to take the derivative of the function. You're going to need to square that answer. You're going to need to add 1 to that answer, and then take the square root of it and integrate that. That's what you have to do. All right.
This is
So in your formula sheets, that's the very first thing. If y is some function of x, and we want to figure out the arc length, we want to basically take this off the page and straighten it out and figure out how long it is. The formula is the length will be the integral from a to b of 1 plus, now I put in this first one, I put dy dx. That's the first version of the formula, but I did f prime of x over here on the second version. These are equivalent, dy dx and f prime of x. You can use either one there, okay? Okay, was
Does
there
it
a
matter
question?
which version of the equation we know when we end up using it?
No, just remember that what's in here is the derivative, all right?
Okay.
Let's do a super, super easy one, okay? Let's do a super easy one to start. Let's say you're given, I want you to find the length of f of x equals 2x on the interval 0 to 3. Now, I'm doing something very easy because we're actually going to be able to figure this out on our own without any calculus first, because that's a straight line, isn't it? So if I were to just think about what this would look like, I have the function 2x, which is a line that has a slope of 2, so it goes like this. And I'm only looking between 0 and 3. So I'm starting out at 0 here. I go out to 3. When I plug 3 into that function, I get, what, 6, right? Right? So what we're trying to find here is this length from here to here. And that's a straight line, isn't it? I mean, so we should be able to check it real quick. We know this distance from here to here is 6, right? And we know this distance from here to here is 3. So if we said this is L, we know that 3 squared plus 6 squared must equal L squared, which means the square root of 9 plus 36 equals L. And that's what, 45, root 45? That's how long that is. Do y'all understand that what I'm doing over here has nothing to do with calculus? It's just algebraically, because it's a line, I can find what the length of that curve is between 0 and 3 on the x-axis. Now let's do it with calculus, and we better get square root of 45, right? We better get square root of 45. So this is a function of x, right? That's a function of x. So what I'm going to do is I'm going to use this formula, integral a to b, square root of 1 plus whatever the derivative of the function is, that quantity squared dx. So to do that, on the side here, I'm just going to start writing things down that I need. First of all, the derivative of f, well, that's just 2, right? That's just 2. Derivative of 2x is 2. I need to take that derivative and I need to square it, right? Which gives me 4. And then I'm going to take that and I'm going to add the 1 to it. And that would give me 5, right? And so that's what's going to go underneath the square root, right? That's what's going to go underneath that square root. So this is going to become integral. I'm going to go from 0 to 3, right? Square root of, well, we just calculated all this over here to be just the number 5 and then dx. Still good? What is the antiderivative of the square root of 5? It's a constant, right? So what's the antiderivative of a constant? The constant times x, right? So like the antiderivative of 5 would be 5x, but it's root 5, so it's root 5x. And I want to evaluate that from 0 to 3. So if I plug 3 in here, I get root 5 times 3, and then minus, and if I plug 0 in here, I get 0. So my answer is 3 root 5. Put the 3 in front of the root 5, which is exactly the same as root 45, because that's root 9 times 5, and then the 9 can come out as 3. So you get the same answer, which is good. I mean, you should, but obviously you probably wouldn't want to do the calculus for finding the length of a straight line, right? You don't need calculus for that. But this just shows you that it looks like it works, right? So let's do something a little more a little more interesting. Okay, a little more interesting. Now, I must warn you that because the formula is so complicated in terms of what you have to do, derivative squared plus 1 square root, that if I just give you like a random function, it most likely you're not going to be able to integrate it. Like you're not going to be able to find the length. Like most likely you're not going to be able to. Because when you put things in there, it's just not going to, the techniques of integration, you know, aren't going to work. So the problems that we can do by hand have to be picked very special. Okay, they're very special problems that are designed so that they'll work for you. So let's do this one. Let's find the length of this curve. Find the length of y equals, let's do this, 1/3 x cubed. Oh, you know what I'm gonna do? Give me a moment. Because these problems have to be picked so special, I'm gonna pick one from another textbook. Okay, let's do x cubed. Let's do 1/12 x cubed plus 1/x. And I want this on the interval 1 to 4. Let's look at it real quick. Let's see what this thing looks like. So if we were to take x cubed, divide by 12, plus 1/x, and we only look at it from 1 less than x less than 4, right there. We want to know how long that curve is, right? Not the area underneath it. We're not rotating around any axis. I want to know how long that curve is if you took it off the piece of paper and stretched it out. Okay. So I don't need the picture. Okay, I don't need the picture to do this. All I need is the calculus. So I know I'm going to be using the formula integral a to b square root of 1 plus whatever the derivative of that function is squared dx. All right, so now my scratch work. I need the derivative of the function. Well, I'm just going to call it y prime. Is that all right? Instead of me calling it, you know, f prime, I'm just called y prime. What is the derivative of this? So this is back in easy calculus, right? 1/4 x squared, right? That's derivative of that. Be careful on this one. Don't tell me natural log of x. You're giving me the antiderivative. Derivative of that should be -1/x squared. How did I do that? That's x to the -1, and then I took the derivative. -1 comes out, x to the -2, and then I drop the x to the -2 back down. So that's my derivative, right? Shit, that sucks. I've got to now square that derivative, right? I've got to square it, which means I've got to multiply it times itself. Ugh. Got to multiply it times itself, which means I've got to like FOIL this out. So let's do that. I multiply here to here, get 1/16 x to the 4th. Here to here, I get, what do I get when I do that? What's 1/4 x squared times -1/x squared?
Isn't that just -1/4?
-1/4, right? The x's cancel, right? The x squared on top cancels with the x squared on the bottom. And then when I do this one, the inner one, I think I get the same thing, right? They cancel again, I get -1/4. And then when I do the last one, I have a negative times a negative, so that's positive. 1/x squared times 1/x squared is 1/x to the 4th. Eugh. Clean it up. 1/16 x to the 4th Negative 1/4 minus 1/4 is negative 2/4. That's the same as negative 1/2. Geez, okay. That's my derivative squared, right? And don't I have to add 1 to it also? And then take the square root of it and then integrate that? Crap. Okay, so that was the first part. This is the second part. Let me go ahead and add 1 to it. What's 1 plus that derivative squared? Well, if I add 1 to that, right, I'm adding 1 to that because that's what I'm supposed to do underneath that integral at some point. All that happens here is the negative 1/2 and the 1 go together and become positive 1/2, which means I've got 1 over 16x to the 4th. Doesn't matter how to write this, plus 1 over x to the 4th plus 1/2. Any questions on how I got that or where we are? And you look at that and you're like, crap, man, I've got to integrate that, right? And don't forget, it lives under a square root. So here we go. Integral 1 to 4 square root of 1/16 x to the 4th plus 1 over x to the 4th plus 1/2 dx. Yikes, right? That looks terrible. I mean, if the square root wasn't there, I wouldn't care, right? It would be easy if the square root wasn't there. And you can't go just squaring it just out of nowhere. You can't do that. We cannot use trig sub either because this doesn't look like the trig sub thing, right? Trig sub, you need like a squared plus u squared or a squared plus x squared, a squared minus x squared, or x squared minus a squared underneath the root. This is not a quadratic like that. So, you know, what do we do? Well, I told you these problems are very special, right? They're made just for you so that they'll work. So there's something more we should be able to do here to make this work. And what it is get a common denominator. We need to come back over here. Okay, I'm gonna just kind of put a question like, what the hell? So I'm gonna come back over to this and I'm gonna continue working this algebraically, and I'm gonna try and get a common denominator. So let me write it this way. This is x to the 4th over 16 plus 1 over x to the 4th plus 1/2, right? That's really what this is. My common denominator will be 16x to the 4th. So I need to turn all my denominators into 16x to the 4th. So I'm going to multiply this one by x to the 4th over x to the 4th. What do I multiply this one by? Top and bottom.
16.
16, so 16 on the top and bottom. And then here I need, what, 8?
8x to the 4th.
X to the 4th. Right, would that work if I did that? So what's my new numerator? These two together, right? X to the 8th plus this 16 times 1, 16. Plus this times 1, which is 8x to the 4th, all over the common denominator, 16x to the 4th. Now you look at that and you're like, well, does that even help? That looks worse. I'm going to put it in descending order. And let's see if anyone can recognize what I can do here.
Looks like you could factor in x, x squared from all on top.
Well, this one doesn't, 16 doesn't have an x
Oh,
squared.
yeah, never mind.
Squint your eyes. What does this look like? I mean, this
Isn't
is
it
like,
The
x
degree is
plus
greater,
4
so
squared?
You can throw the root on top and throw the root on bottom.
well, the root's going to come in, right? We are going to bring that root in. We are going to bring the root, and we can do that on the top and bottom. But what about this numerator?
Doesn't it factor into like a perfect square? Wouldn't that be x
is.
plus 4 squared?
This is x to the 4th plus 4 times x to the 4th plus 4. over x 16x to the fourth. You have to see that this right here is like a, this is like a perfect square trinomial. That's what it kind of is. Except that it's not x squared and x, it's x to the eighth and x to the fourth. So just run through this. If you multiply this out, you get x to the eighth, then you get 4x to the fourth, and another 4x to the fourth, that's 8x to the fourth, and then 4 times 4 is 16. So that really is just x to the fourth plus 4 squared over 16x to the fourth. Okay, so I actually am happy to see that, because if I come back here where I was kind of stuck, I know now that all of that becomes this, right? Sitting underneath the square root. Hey everyone, I have no idea why I put dy here. Do y'all see that dy? I have no idea why I put dy there. Well, I do know why, because if it was a function of y, we would do it that way. Dx, sorry. So do you see why all of this algebra here was helpful? When we take this square root, like Lewis said, we can do the square root of the top and bottom separately. So this becomes integral 1 to 4. So the square root of the top kills off the squared. So all we're left with is x to the fourth plus 4. And on the bottom, well, wait, I can take the square root of 16, that's 4. And I can take the square root of x to the fourth, that's x squared, dx. No more root. That is something I don't mind integrating, because I can now split this into two fractions, x to the fourth over 4x squared plus 4 over 4x squared, right? You have two terms on top, one on the bottom, so it can split up. So this becomes integral 1 to 4 of, let's see, on this first one, these cancel out. You just get an x squared and you have a 4 on the bottom. So I'm going to put 1/4 x squared there. And then plus on this one, the 4's cancel. I get an x to the second power on the bottom. So I'm going to write that as x to the -2 dx. And now I'm ready to integrate. The antiderivative of that is going to be 1/12 x cubed minus, I'll just put 1 over x, evaluated from 1 to 4. So I'm just using the power rule for antiderivatives, right? Adding 1 to this, putting a 1/3 out here. Here I'm adding 1 to this, that gives me -1. I'm putting a 1 over -1 out here, that gives me this. And now you plug in 4 and you plug in 1 and we see what we get. So 4 to the third power, 64 over 12 minus 1 over 4. Now we plug in 1 and we get 1/12 minus 1 over 1 is 1. Let me just tell you what that answer is. The answer here is 6. That's how long that curve is, 6 units. Yuck, right?
Yeah, that one was
Right
kind of
here.
nasty.
Yeah. Not pretty. Not pretty. But these problems, like I said, they have to be made, special for you so that they work. So be prepared for some algebra. Let's see here. Which one do I want to do? I don't think I've ever done one like this before. How about this one? How about find the length of the curve? Y equals sine x minus x cosine x on the interval 0 to pi. So this is y equals sine x minus x times cosine x. And we want that on 0 less than x less than pi. How long is that curve? That's the question, right? How long is that curve? All right, well, we already know the formula that we're going to need, right? So we need to find the derivative, we need to square it, we need to add one, we need to throw it under square root and pray, I guess, that we can do it. All right, so the derivative of this is what? Cosine x, that's derivative of sine, minus, and now when you do this, you have to take derivative of those, right? That's a product rule in there. It's a product rule. So it'll be the derivative of the x, which is 1 times cosine x, plus now the derivative of cosine of x, which is negative sine x, and then times x. That's product rule Cal 1, right? We're all okay with that? I hope. This is cosine x, let's see, minus cosine x, because that distributes, makes that a minus. And then over here, this was already gonna be a minus, and we distributed that. So that's going to become plus x sine x. That okay? Then this would be y prime. Now y prime equals, let's see, the cosines cancel. And we just have the positive x sine x. I don't know about this one. It's gonna be weird. Okay, so now we take that derivative and we need to square it. We square that, we just get x squared sine squared x. Any questions there? Now we need to add 1 to it. So 1 plus this would be 1 plus x squared sine squared x. And I've got to put that under a root. So let me do that. I'm going to go integral 0 to pi root of 1 plus x squared sine squared x. Yeah. Dx. So I just pulled this problem out of this other textbook. Hold on. Oh, okay. I'm sorry, I misread the problem. It says, do this and then use a computer to do the integral. I was like, okay, there's no way we're doing this integral. I can just tell by looking at it. There's nothing we can do for this. All right, so this is a good example of, yeah, you can set it up, but then you need some sort of numerical solver for it. Yeah, so let's do it. Let's go to, I don't know, are there any math programs that you can do integrals on? I'm kidding. You all know about them already. All right, so here we go. I'm going to scroll that up. I'm going to Wolfram Alpha. Let me do it this way. I want to do the integral. I want to go from 0 to pi. And I want to do the square root of 1 plus, I'm going to type it in this way, x times sine x, that whole quantity squared dx. Oops. Dx. See the way I type that in? Oh, it already did it. 4.6984 is the approximate length. Now you might wonder, like, how did the computer do that, right? Like, how can the computer do it, but we can't do it?
Yes.
Yeah, well, they use series. They use what we're going to talk about in chapter 8. All right.
Okay, so we'll be able to solve this one later,
We would be able to in theory,
in theory.
but we would definitely want to use a computer to do it because it can do the computations a lot faster than we can. So could we theoretically by hand do it? Yes,
Okay,
but it would just be kind of messy.
so
Go ahead.
is learning power series, is it one of those more of almost a formality thing of so that we could effectively understand what the computer does because the things that you do with it is so awful?
The power series are necessary because it allows us to take complicated functions and expressions and make them something a lot easier to work with.
Gotcha.
And we can be as precise as we ever need to be with those. So
Yeah.
because what you're doing is you're taking any function out there and you're turning it into a bunch of powers of x being added or subtracted together.
Okay.
So you're basically turning any function that you ever need to work with into a polynomial. And there's a famous theorem called the Weierstrass theorem. I'll mention it when we get to chapter 8.
Is it that one where there's no, like, it's not continuous at any point or something like that?
Okay, so that's a function. It was tied into the same person, but this is a theorem by that same mathematician
Oh,
that says that if you give me any function, we can approximate it with a power series as closely as we ever need to. And so
Okay.
that means that, you know, the computer can do the power series. Watch, I'm going to show you something. I'm going to get rid of this. Let me delete that. And I'm going to try and have the computer do the antiderivative of that without the limits of integration. In other words, I'm not going to, I'm doing the indefinite integral,
yeah.
not the definite. When I do the definite is going to give us a numerical value. But if I do it as an indefinite, where it's going to try and give me a function as an answer, I think it's going to have a problem with this. It's probably going to introduce an error function or some sort of like Gauss function or something. Let's see. It's thinking. It's having trouble. Did I do something wrong? Let me try it again. It can't handle it. Yeah, it's having a hard time, right?
Doesn't know how to deal with it without the limiters.
Yeah, but I'm actually surprised it's not at least giving us. Okay, so let me do this. Let me take the integral off of it, if I can. Okay. Let me just get rid of that. Let me take the integral off of it. Let me just type in the square root of 1 plus x times sine x, that quantity squared. And I'm going to see if it will just give us the power series for that. Now, we haven't even talked about power series, but let's see if the computer is smart enough to tell me that there's another way I can write this. There it is. There's the series expansion of that function. So notice that there's a way that you can write this, okay? There's a way that you can represent this function as a different function that is just a polynomial, but it goes forever. Let me see if I can. No, I can't go any further, but it gave me at least the first 4 non-zero terms of its power series. So if I needed to integrate this, like if I needed to integrate this from 0 to pi, instead of integrating this from 0 to pi, I can integrate this from 0 to pi. That's why the computer was able to get us an answer for the definite integral from 0 to pi, whatever it was, 4.69. Okay, so that's what chapter 8 is going to be about. We're going to try and figure out how you turn a function into its series, into its what's called its Taylor series or Maclaurin series. All right, but let's stay tuned.
So I had a quick question.
What's that?
I had a quick question. Can you, so when you're integrating, can you set the boundaries from like 0 to infinity? Will the length to just be infinity, or can it be, will it be an infinite number, or will it actually stop somewhere? Like how when we took
That's a really good question. What do you think?
I think
Can
it'll
you
go on forever.
possibly draw a curve that starts somewhere and goes forever, and the length not be infinite?
Yes.
You think you can?
Maybe. That's why I asked you.
So
But
you have a pencil, right? You start drawing to the right forever. I don't care if you're squiggling up or down or whatever. And then we want to straighten that out and measure how long it is. I think this is your question.
yes.
Is that always infinite?
Well, I'm thinking of like the function of 1 over x, and
Okay.
it goes out into infinity, but it gets really close to 0.
Does that impact the length though?
I'm thinking
this
about
goes
it.
like
I don't
this.
think it does.
Does as it flattens out, does it change the fact that like the distance between those 2 points, that's some number, right?
Yeah.
And it's not getting smaller. As you go to the right, I agree that the height of the function's getting smaller, but if you're measuring this length, it's going to be infinite, right?
Yeah.
So to answer your question, if you do any integral for arc length, right? And you go from like 0 to infinity, as long as it's a function of x that exists out there, then that should be infinite.
Okay. That's interesting.
Yeah.
Like the area can be definitely.
Area is different. Area is different because these areas get smaller, right? They're getting smaller and smaller and smaller. Whereas if you go out to the right and you draw forever, your lengths aren't getting smaller, right? Because you just keep on drawing and drawing. Yeah. Essentially, it would become almost a straight line. As you go to the right, if it gets smaller, you get like this function right here. The red curve to the right is almost like drawing the x-axis practically, which has an infinite length to it.
Is this, I heard about a paradox of something.
Yeah, we're going to do that
trumpet-
today.
The trumpet.
Maybe if we have time.
Okay.
Also, quick question. This has brought to my mind an additional concept, which is, I guess it's also possible to have a line like this, a function like this, where the length of it approaches infinity without our values approaching infinity. Like if you have a vertical asymptote at 3, if you have it from 0 to 3, the length would be infinite, correct?
Well, yeah, but you could do something even easier than that. You could do something like just the graph of sine of 1 over x. And you look at that graph just between like 0 and 1. Like
Yeah,
this
that's
graph
right. Doesn't have
infinitely-
infinite length in between.
infinitely squiggles. And so that should have an infinite arc length between 0 and anywhere really. 0 to the right anywhere. But
I hate this function.
yeah, well, that would be like an improper integral.
It's
though.
so gross.
Yeah, it's an interesting function though. Okay, so let's look at the notes here. Everything we've been doing, these have been y is a function of x. All right, and then we had our formula. What if we have it the other way around, where x is a function of y? Well, good news. Not much changes in the formula, except that, wait a minute, except that I have a typo in my thing. Do y'all see my typo?
Yeah, dy.
It's dy. It's dy. You're basically going to be doing the exact same thing, but with respect to y, not x. Not sure why I forgot to do that. Let's see here. Yeah. Okay. So the only difference when you have a function of x is a function of y is that your limits of integration are going to be up and down, c and d, instead of left and right, a and b. And then you still need to take the derivative of the function and square it and add 1 and take the square root, you just be doing it with respect to y. Okay? All right, I want to do one more example before we move into the next section. Do you remember I have already proven to you in this class the formula for the area of a circle in general, right? We proved pi r squared is the area of a circle. We proved that the volume of a sphere or volume of a ball is 4/3 pi r cubed, right? We proved both of those. I'd like to see if it's possible for us to prove the circumference of a circle. So if you take a circle, okay, of radius r, we know the circumference is 2 pi r, right? That's a formula that's been given to us. We all accept that as truth, but let's prove it. Let's prove it. So we go back to this whole idea that, remember, this is a circle, x squared plus y squared equals r squared, right? That's the circle that we're talking about. When we did this before, go back in your notes. What we did is we solved for y, and we got square root of r squared minus x squared. So how do you think I'm going to go about proving the circumference, distance around? How do you think I'm going to do that?
It'll be an arc length of that.
But let's just take maybe just this top right corner of it. Let's find the length of just that piece. Right? The length of just that piece. So that means my integral, what are we doing here? We're proving, right? Prove circumference equals 2 pi r, right? So I'm going to take this curve. I'm going to do this integral. It's going to be the integral. It's going to go from 0 to r because I'm going to go from here to here. And then what I need is I need the derivative of this thing squared, right? And all that stuff, plus 1 underneath the root, all that crap. Let's do that. So what is y prime? So we have to take derivative of this, right? So derivative of the square root of this should be 1 over 2 square roots of that thing, r squared minus x squared, times the derivative of what's underneath the root with respect to x. So derivative of r squared is 0, derivative of negative x squared is negative 2x. Oh, I forgot to put the prime here. That's my derivative. Let me clean it up. Negative x on top, square root of r squared minus x squared on the bottom, right? That's what that is. 2's canceled. Do you have any questions on what I'm doing right now?
Isn't r a constant? You could take that out.
It is a constant. That's why when I took the derivative of what was under the root, I just got negative 2x squared, because the derivative of r squared would be 0. What's wrong, Louis?
Can you say that one more time?
So when I'm doing the derivative of this, right, I have to do chain rule. So first I deal with the square root. So the derivative of the square root of this is 1 over 2 times the square root of that thing. Right?
So sorry.
Then I
about
say,
that. I didn't know that's where you were leading. My bad.
okay, no, I make sure you understand it, right? Then I take the derivative of what's inside the root. The derivative of r squared is 0. The derivative of negative x squared is negative 2x. That's this piece.
So I'm referring to like equals to negative root rx squared, but you can't take that because it's a constant.
That's right.
Big, whatever.
So that's y prime, right? That's y prime. And now I need to square it, don't I? Ooh, squaring it's nice. I get x squared on top. I no longer have a negative. Ooh, that's real nice. I get r squared minus x squared on the bottom because you square the square root, it goes away. Beautiful. Okay, I need to do 1 plus that derivative squared. So if I do that, I'm going to do 1 plus this thing. What do you think I'm about to do with this?
Find the common denominator.
Get a common denominator between these two. So when I do that, I'm going to do r squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared. So there's my common denominator. Do y'all see what happens up top?
Yeah, we can cancel out the x squared.
So you just get r squared over r squared minus x squared. Yeah. That's the thing that's going to go under the root. So I think I'm happy about that. I'm going to come back over here to the integral. As we go from 0 to r, I have the square root. On top, I have r squared. On the bottom, I have r squared minus x squared dx. Any questions?
Isn't that an identity? R squared minus x squared? And you could throw it in for maybe like an actual, like you can solve it from there.
Well, we don't know what r is. We don't know what x is. Not sure what you mean by identity.
Like we can use a u sub here, like a negative x root r squared minus x squared. X squared turns into 2x, take out 1/2.
Yeah, if you have it, but do you have an x somewhere else?
Yeah, it's on top. It's the
Where?
negative.
No, it's gone. It was gone. That x squared's gone.
Oh, that's what happens whenever you square root it.
Right. When we put those two together, the x squareds went away.
Oh, I'm so sorry. I'm looking at the top. My bad.
Yeah, no, remember, this was just y prime squared. I hadn't added the 1. When I add the 1, then we get this expression. Look, actually, this is a lot cleaner than it's cleaner than it looks, because you can do the square root on top and bottom right now. What happens if I do the square root on top? I just get r, right? If I do square on the bottom, I get square root of r squared minus x squared, right? Dx. That r is a constant, so it can come out of the integral on the top. That leaves me with 1 over the square root of r squared minus x squared dx. And that I can do with trig sub. That's basically 1 over the square root of a squared minus x squared. Now, I'm not going to do the trig sub because time. What I'm going to do is I'm going to refer you back to your formulas. And on your formulas, there is actually a formula for this one. It is formula 16.
You know what? That's why I kept on wanting to do trig sub. Like I felt it in my
Yeah.
gut and to shoot it.
That's what I thought you meant, that trig sub. So here we go. So we have this, we basically have this right here, right? Where for us, the R is the A is the R here. So that's R here like that. And of course, the U is the X. So this should turn into R, right? I'm taking the antiderivative now, R times inverse sine of X over R. That's my antiderivative, evaluated from 0 to R. And we're going to now plug in R for X. So I'm going to have two things. If I plug in R for X, I get inverse sine. Let's see, R over R would be 1. And now I plug in 0 into this. So I'm going to have R inverse sine of, well, 0 over R would be 0. We're almost there. We need inverse sine of 1. So at what angle on the unit circle is your y coordinate 1?
5/2.
5/2. Okay. And then minus, now this one is saying where on your unit circle is your y coordinate 0?
0.
0. And of course, because it's inverse sine, we're restricted to only the first and fourth quadrants. So this will be 0. That'll just kill this all out. And so your answer here is pi over 2 times r. Right? That's your answer. But this was only 1/4 of the whole circle, right? It was only 1/4. It was just the first quadrant. So what I need to do is take this answer and multiply times 4, And that gives you 2 pi r. There it is. So we have now proven in this class that the circumference of a circle is 2 pi r, the area of a circle is pi r squared, the volume of a sphere is 4/3 pi r cubed. What do you think's coming next?
The surface area of a sphere.
Surface area. Surface area. But we need to start talking about surface area before we can go do that one. All right.
I will say that sounds like it will be the worst one.
Sounds like it would be the worst, right? And I agree. It does sound bad.
But I will say though, with my experience, seeing as the volume of the sphere was the easiest one to prove,
Yeah.
it might not be as bad as this one even.
Yeah, it's going to be actually easier than this one.
We'll have to learn some brand new weirdo method, and then once we learn it, it'll be like 3 steps.
Yeah, exactly. Oh, there's another way of doing all of this stuff in Cal 3 that makes it even more child's play, like even easier. But you have to go into polar coordinates. You have to switch your coordinate system over from Cartesian to polar. But that's for Cal 3. Okay, where are we at?
So our final is just gonna be proving the circle 3 times. Gotcha.
In a different universe, yes. All right, let's talk about surface area now. All right, so I've got an animation here for you on this. Can you all give me just a minute? I ran out of drink. I need to just refill. Take a minute for yourself. We'll be back in a minute.
Hunter, go get some water, dog.
That's what I'm doing.
Go get some water. Go get some water, Ricardo. Tell your dog to go get you some water. I know you trained him. You can
Yeah,
fucking.
I got my energy drink.
You too, Brandon. I'm looking at you. Oh, he's already got his shirt.
Already got it. Already got it.
Hey, Ricardo, are you taking any summer classes?
Yeah, I'm taking it's hard to say. It's an arts class, Rose. So
Let's go.
What are you talking about? This is art right here.
this is beautiful. Okay, this is the difference. So taking a stupid arts class in the summer.
I want to see your drawings. They'll teach you how to draw better.
I think it's an appreciation to art, so I don't think I'm going to be drawing. It's more like of
Wait, like art theory
something like that.
or art history?
No, it's like appreciation of art.
Dude, they're just as bad. Everything's subjective.
Yeah, gross. No.
Okay, y'all ready? Surface area. We have a curve. Think of this curve now, all the different things that we can do with it, right? We can find the area underneath this curve. We can rotate around the x-axis, find the volume. We can rotate around the y-axis, find the volume. We can take it off the piece of paper, stretch it out, find the length, right? All those things are possible, theoretically. But now what we want to do is we want to take it, imagine again that it's 3-dimensional space. We want to wrap it around the x-axis. And instead of finding the volume, we want the surface area of that object. So volume and surface area are 2 different quantities, right? The volume of something is how much is in it. The surface area is like a measurement of how much area there is on the outside. So volume is a 3-dimensional unit, where area is a 2-dimensional unit, right? So we want to know the surface area of this. So, just like before, we got to figure out a way of doing this in a way that we can use the integral. So here's the approach. We're going to take that curve from A to B. And we're going to do the same thing with the little rectangle, right? We did a rectangle, but we're just going to take one little piece of this Okay, one little piece of that, and wrap that piece around the x-axis. If I wrap the piece, not the rectangle, just the top edge of it around this, I will get something that looks kind of like a rubber band. That's terrible. Okay, it's a rubber band, all right? It's not solid, it's not a washer, right? It's not a disc, it's a rubber band. And what I want to know is what is the area of that rubber band? That seem reasonable? To just, if I could find a formula for the area of this, whatever it is, then if I could just add them all up, all the rubber bands as I move from left to right, then I will have the area of the whole surface. So I do what I did before. I'm going to just come in here with my scissors and cut the rubber band and open it up. All right, now when I do it, I'm actually going to lay it down this way. Here's my rubber band laying here. Okay, lay it like that. There's my rubber band. Now, the distance from the axis of rotation to the edge of the rubber band, that distance right there, isn't that just the height of the function? That's how tall the function is, right? From here to here, that's f of x. So that should be the radius, right? I did this before when I had that other example where we had taken it and we had cut it open, right? And we said, well, how long is it? It's the circumference of this thing, which is 2 pi r. Hey, we just proved that formula, right? So isn't this distance from here to here just 2 pi, 2 pi times the radius, but the radius is f of x? Yeah? You buy that? Tricky part, how thick is it?
dx.
I know you want to say dx. I know you want to say dx. I mean, that seems natural. But think about it. There was this curve, right?
Oh, it'd be the hypotenuse with
Which
dx and dy.
is,
Square root of dx squared plus dy squared.
which is exactly the formula we just used,
Yeah.
right? Wouldn't this be not dx, but the arc length? It's the length of that little arc, which would be the square root of 1 plus the derivative of the function squared dx. That's how long, that's how thick the rubber band is. So the area would just be those two multiplied together, wouldn't it? The area then would just be these two multiplied together. Further, if I wanted to find the total surface area, I would do the integral. So what do we got? The total surface area. Let me get back up here. Total surface area. Surface area will be the integral. I'm leaving a space there for a reason. It'll be 2 pi times the function f of x times the square root of 1 plus the derivative of the function squared dx. That is this piece here times this piece here. Any questions as to where any of that came from? So this is like circumference, right? Circumference times thickness. Circumference times thickness. 2 pi is a constant, yes? 2 pi is a constant. Can bring it out. Oh, I forgot my a to b. Sorry, forgot my a to b. A to b. So that gives us our final formula, which on your formula sheets, or on the sheet I showed you at the beginning of class, 7.2, here are your two arc length formulas with the typo. Remember, there's a typo right there. And then it goes to area of surface of revolution. And this is if you're rotating around the x-axis, the very first formula, 2 pi integral a to b f of x square root of 1 plus the derivative of the function squared dx. That's the formula I'm showing you right now if we rotate around the x-axis. Good news, we will only rotate around the x-axis. We will not do lines above it or below it. for surface areas. We could, but we don't do that in this class. We just kind of stay at the x-axis for surface areas.
Isn't it like the same thing except just a little bit more?
You have more that you have to do because you have to figure out, like, you know, that it's kind of like the you have to find the radius. The radius would not be f of x necessarily. It would depend on where the axis of rotation is. So we could do it, but it's just we're not going to do it. All right.
Cool.
Okay. So what is the big difference between this formula and the one that we had for arc length? There's really only two minor little differences, right? We have a 2 pi in front instead of no 2 pi, right? And the f of x. If you get rid of those, you have arc length, right? That's arc length. That's surface area. Very similar, right? Very similar. Questions? So should we do an example?
Yes,
Yeah, let's
please.
do an example. Trying to think of one. Okay, yeah, let's do this one. Find area of surface if y equals sine x on 0 pi is rotated about the x-axis. Okay. If it's rotated about the x-axis. I don't think you need a lot of guidance here in terms of what this looks like, right? That's your sine function. Well, that's not that great, but that's your sine function on 0 pi, right? We are rotating this around the x-axis. And we're trying to figure out what the surface area of that is. Kind of looks like a football a little bit, right? If you rotate that around the x-axis, trying to find the surface area. So I already know I'm going to need the formula 2 pi integral f of x square root of, oh, sorry, a to b, 1 plus the derivative of the function, that thing squared dx. So let's go do some scratch work here on the side. Our function's derivative, I'm calling it f of x, even though it was given to me as y equals, I'm really just saying, okay, that's f of x. That's our function. All right. So the derivative, that's cosine x. Ooh, I like that. Not that bad, right? I need to square it. Well, that's just cosine squared x. I'm not unhappy about that. I need to add 1 to that. That's 1 plus cosine squared x.
Is that a trig identity?
It
If
should
it was
be,
a
I think that's a
minus,
trig
well,
identity.
If
Oh,
it was minus, it would be. If that was minus, it would be sine squared.
Yeah,
That's where it would get me.
that's a shame.
Boom.
That's a shame. It is a shame. But hold on, don't feel too discouraged yet. We've got integral 2 pi, integral 0 to pi, right? We're going from 0 to pi. Now, here's the cool thing. F of x, right, goes in front. Well, f of x is sine x. Square root of 1 plus cosine squared x dx. Now, this still doesn't look great, but that integral is doable. I'm just going to look at it over here. Forget the 2 pi, forget everything else. Let's just try this as an indefinite integral. If I asked you to find the antiderivative of this, could you do it, and what method would you use? Go back to the very beginning.
Could you
You
just
see
use u
something
sub
in
in
its
there?
something in its derivative, right?
Yeah,
If I let u be cosine x, what's the derivative of cosine x? Negative sine x dx, right? Do I have a negative sine x dx on the outside? Kind of. I need to make this a negative du and a positive sine x. Now I do. So I could rewrite this integral. The sine x dx, that part turns into negative du. So I'm putting negative on the outside du. And then I have square root of 1 plus what? Well, cosine x is u, right?
yeah,
So
1 plus u.
1 plus u squared, right?
Trig identities.
Trig integral, a trig substitution, trig sub at this point. But I'm going to see if we have a formula for it. Let's see. Do we have a formula for that? Ah, we do right here. If we have the square root of a squared plus u squared, let me grab this formula. It ain't pretty. It ain't pretty, but it is a formula, right? Ah, that's really not pretty. So this says that if we have, let's see, for us, the a squared, that's 1, right? So a is 1 for us here. And the u, well, the u is u, right? U is u. So according to this, this should be negative. Don't forget that negative that's out in front of all this. And then the antiderivative of that should be u over 2 square root of the a squared plus u squared. So that's just going to be 1 plus u squared. Plus, okay, a squared over 2, but a was 1, so that's 1 over 2. Natural log of u plus the square root of 1 plus u squared plus some constant. That's my antiderivative, right? That's it right there.
Yeah, and then we got to substitute back in our u.
Yeah, all the u's get turned into cosines now.
Ugly.
So let's go back to this now. So here's where I am. The antiderivative of this is the 2 pi that has to come down. And then this, so I'm going to put the negative in front of the 2 pi, right? That negative right there, I'm putting it in front of the 2 pi. And then I'm going to have u, which is cosine of x over 2 times square root of 1 plus cosine of x squared plus 1/2 natural log of cosine of x plus the square root of 1 plus cosine squared x. All of that evaluated from 0 to pi. What is cosine of pi?
-1.
-1. What is cosine of 0?
1.
+1. So there's going to be a lot of 1s and -1s getting plugged in now. So this becomes 2 things subtracted. Let's see if we can't get this. I have -2 pi. Okay, let me plug in pi here. Cosine of pi you said was -1, so -1/2. And then cosine of pi is -1, but then I square it, that's +1. +1 is 2, so you get √2 there. I'm gonna turn off my grid lines because it's kind of getting in my way there. Plus, let's see, 1 over 2 natural log of, let's see, cosine of pi you said was -1 plus, and then this would be √2 again. I do the same thing now, plug in 0. So I get -2 pi. And then cosine of 0 is 1. So you get 1/2 square root of 2 still. Plus 1/2 natural log of 1 plus √2. Okay, we have an answer, right? I'm gonna stop here. I mean, we could try and clean things up, distribute negatives through, but we have an answer, right? We have an actual number. That was a weird one. Dot, dot, dot. Questions?
No, that's a nuts answer.
Yeah, it is, but I
Not
think
the
a lot
worst
of
one we've
things-
had.
Yeah, I mean, this is a weird answer, but it probably is a weird area, right?
Yeah,
Or weird surface area. Let me go back to my
Football shape.
animation. My animation. We took this region, right, and we wrapped it around the x-axis, and we found the surface area. What if we did it this way and wrapped it around the y-axis instead? Different surface, right? Different surface area, right? Different surface area. So how would we go about that? Well, I'm going to save us some time. Scroll down this x-axis rotation. This is the formula I just gave you, right? What if we want a y-axis rotation? Okay, for a y-axis rotation, there are two scenarios. Well, I should go back. When we do an x-axis rotation, this is what you do if you have a function of x. You do the formula that we just learned. But what if it's a function of y? I haven't given you an example of this, but what if you want to rotate a function of y around the x-axis? Your formula changes to this. And that is correct. There's no typos here. All right. So that's how you do a function of x around the x-axis and how you do a function of y around the x-axis. Now, if you want to do y-axis rotations, the question is, do you have a function of x or a function of y? If you have a function of x, here's the formula. Okay, this is the formula if you have a function of x. And then this is the formula if you have a function of y. I can't go through and show rubber bands for all these. It'll just take too long. So what do you say we do a problem? We've got about 12 minutes. What do you say we do a problem where we have a function of y? We haven't done anything with the function of y yet. We say we do one of those. Yeah? Okay, so let me see here. I'm going to pick one over here. Let me see if this book does. Okay, let's do this one. All right, we want to rotate x equals y plus 2 square root of y on the interval 1 to 2 about the y-axis and find the surface area. All right. So first thing I'm going to do is I'm going to ask myself, am I given a function of x or am I given a function of y? So what is that? Function of x or a function of y?
It's a function of y.
It's a function of y because it's solved for x. Okay. So we have a function of y. Now I'm rotating around the y-axis, right? So now I'm going to go to my notes. I want a function of y around the y-axis. So here are my notes for surface area, right? These are the notes for surface area. I'm not doing an x-axis rotation. I'm doing a y-axis rotation, right? And do I have y as a function of x? No, I have x as a function of y. So this is what I want to use. Okay, that's what I want to use here. So I'm going to call this in red here. I'm going to call this in red here my g of y. See, it's some function of y. So according to the formula, I need to integrate 2 pi integral from c to d. C to d are the restrictions on the variable which are given to me in the problem here from 1 to 2. And then g of y, okay? G of y, which is just this, right? That's what goes right here. So I've got y plus 2 root y times the square root of, and now I need to put 1 plus the derivative of the function squared and all that stuff in here, right? So maybe I go do that over here. What's g prime of y? What's g prime of y? What's derivative of y with respect to y? 1.
1.
1. Don't freak out. 1 plus, and now take derivative of this with respect to y. So this is like 1 over 2 root x, or 1 over 2 root y. So you just basically get 1 over root y here. Then you have to square it and then add 1. I'm going to leave the rest of this to you. I just wanted you to see the setup for it, okay? Because the rest of it is just algebra. It will clean up though, okay? It does clean up. Things go away, things get nice. You need to get a common denominator, put things together. Can I leave that one okay? Can I leave you alone with that one? Because I want to show you one more thing with this. You sure? I can stop there? What if we wanted to do the same problem about the x-axis? Please pay attention to this, okay? Please pay attention to this. If I want to go a function of y around the x-axis, then I go back to this. Okay, I'm doing an x-axis rotation for surface area, and I have a function of y, not x. So I'm going to use this formula. Instead. There's one tricky part to this formula. Please, again, pay attention. Please pay attention. You're going to have 2 pi integral 1 to 2. That's still all the same. But do you see this in front here, this y? That y, you're not going to try and solve this thing for y. All you're going to do is put the variable y there. It is just the variable y. And then you do the square root, and then you fill in the rest of this with a question mark, which would actually be the same thing you get in this one. Okay, it's the same thing you would get in this answer, would go in here dy.
Why is
So
that?
that's, oh, sorry.
Say what?
Why is that the case again?
Why is what the case? Why is it a y? Because if you draw a rubber band in this scenario, that's what would happen. There's 4 different scenarios we can have. Function of x around the x-axis or y-axis. Function of y around the x-axis, y-axis. I showed you how to come up with the formula for the rubber band when we had a function of x around the x-axis. Because of time, I can't show you how to come up with the formulas for all. Well, I can, just not here. If you want to look at it some other time, we can. But I only developed the formula for the first one. And for the first one, the very first one we did right here. But you could similarly do the same thing with these. So you're asking, why is it a y in front? Well, that's because that's what will happen with the formula. If you try and draw the rubber band and do the cuts and all that.
All right, cool.
Jonathan, did you have a question?
I was just gonna say, so that's function of y around the x-axis, right?
That was a function of y around the x-axis, yes. And when you do a function of when you do a function of x around the y-axis, the same thing happens. You'll have an x in front. So those are the two kind of weird scenarios. I think we may have time. I don't have much. I have 4 minutes, but I'm going to blow through this like nothing here. I'm going to, let's find the area of the sphere. Find area of a sphere. I'm going fast. So if we have a sphere that has a radius of r, I want to find what the area of that sphere would be. All right, so I'm going to do the same thing I did before. This is kind of getting old. This is a broken record here. I'm only going to take the first quadrant of this circle. That's y equals the square root of r squared minus x squared, because we've been through this a million times now. We're only going to go from 0 to r, right? And I want the surface area of that rotated around the x-axis. So that's the formula, the very first formula I gave you. I want this 2 pi integral a to b f of x square root of all this stuff, right? That's what I want. Okay, so I'm going to go 2 pi integral 0 to r, the function itself, which was square root of r squared minus x squared, right? Times then the rest of the formula, right? But wait a minute, didn't we already do that? We did that. When did I do that? Right here. Do you remember when we were doing it for the arc length? Didn't I have to do the derivative and square it and add 1 and all that? Didn't I already have to do all that? So instead of repeating myself, what did all of that shit have to come out to be at the end? Wasn't it just that? Right? Wasn't it just that? And I pulled an r out. But it was r over the square root of r squared minus x squared. So this really just becomes r over the square root of r squared minus x squared dx. Right?
And those cancel.
That is what, when we look at this formula, see this part right here, that's that arc length part, right? The only thing we've done is we've added this part to it to find the surface area and the 2 pi out front. So what happens here is this whole thing cancels with that. They're gone. The r comes out. So you get 2r times pi outside of the integral. The only thing left in the integral is 1 dx. And the antiderivative of 1 is just x. So this becomes 2r pi x evaluated from 0 to r. Plug in r. What do you get when you plug in r? R for x, wouldn't you get an r squared times pi? And then minus, now plug in 0 for x and it kills everything off. So you just get really 2 pi r squared, right? But that's only one half of it, remember? Because I'm going to take this piece here. If I rotate that around the x-axis, I get half the sphere's area. So I need to double this answer to get the full sphere, 4 pi r squared. Is that the formula? Oh yeah, I did that in like 3 minutes. The area of a sphere is 4 pi r squared. All right, everyone. So what I recommend you do for homework is 7, 4, and 7, 5. There's not, I don't give you many problems here, okay? Really, I don't know. I mean, you could try some more of these. I would say try a few more. I really plan on the test to give you something that you can, because these have to be picked so special for you to work them out. I plan on picking something where the algebra is nice. Like you might have to get a common denominator and put things together, but you know, this is only 3 problems I'm asking you to do here. If you do those, maybe try an extra 1 or 2 from each section, just to kind of see how it goes. But, all right, that's it. We're out of time. Sorry to go over a little bit. Everyone, have a great day. Great weekend, right? What are we, Wednesday? Unless I see you in my office hours, have a great weekend.
Thank you. You too, sir.
All right.
Bye.